Hello, so today we're going to be working through a tutorial on regression analysis, and we're going to be using 911 data and 911 response data and analyze that through geographic weighted regressions. And we're going to use these regression analyses to try to model spatial relationships. So the regression analysis will allow us to model, examine, explore spatial relationships because we want to understand the factors that are behind the spatial patterns that we observe. And the whole point of a model is to try to predict outcomes based on this understanding. So we try to model what's happening in current time, and that model we construct, we try to manipulate it in order to see how that will impact future results. We're going to be using two main models. One is ordinary least squares regression. The other one is a geographically weighted regression. And this is all going to be located under the spatial statistics tools, under the modeling spatial relation tool set. So we're going to find this all in our ARC toolbox, spatial statistics tool, modeling spatial relationships, and we'll see the GWR, geographically weighted regression, and the ordinary least squares, or OLS. So to understand GWR a little bit better, we had to kind of understand just general regression a little bit better, multivariate regression. So for example, we're going to look at this model here, this regression model. And what we have here are various factors, a dependent variable, which is going to be our y variable. And this is what we're trying to model or predict in our equation. So this is the results. So in this example here, we're using residential burglary. So that's the factor we're trying to result. And then we have explanatory variables. That's things that we believe to have influence. So we think that, for example, income might have influence, or number of vandalism incidences, or households, for example. And that's what we're going to see here with the x1 and x2. So those are going to be variables that we plug into our regression analysis. And then we have coefficients in front of these variables, like here's beta 1, beta 2, beta naught. These beta values are what are computed during our regression, and they reflect the relationship of this explanatory factor to the dependent variable. So whatever beta 1 value we have here, that explains how much impact that this explanatory factor has on the y. So if we increase x by 1 unit, the beta value is going to increase the y by that much of the beta value. The beta naught value is the intercept of the y-axis. So pretty much when all factors are 0, and you can kind of see that as kind of like a baseline. And then our last variable will be our residual, the portion of the dependent variable that isn't explained by the model. So this is our random error. This is either it can be random or it can be part of explanatory variables that we didn't take into account. So these different parts of the equation are going to help us in analyzing our spatial data. So whenever you do your regression analysis, you'll have different kinds of beta values, and then you'll see here, like for example, if it has a positive slope in the line, these beta values can also be seen as slopes right here for these x variables. So whenever you have a positive trend, this will show like a strong positive relationship. Whenever it goes down like this, it shows a strong negative relationship. So as you increase that factor, your y will decrease. And then of course there's no relationship where it's near flat. So no matter what you do to the x variable, the y doesn't really change. And these kind of things we will be looking at. This is going to be seen as like the positive or negative sign. So for example, if we have a positive sign in front of our beta coefficient here, this beta, if it was a positive value, you're going to expect like this. And if it was a negative value, you'll expect this one. And then if it's really close to 0, you'll see something like this. So for example, in our model, we have beta 1 with income as the factor. If we got beta 1 to be a negative value, that would mean that as median income in the neighborhood goes up, the number of burglaries go down. So that's how you say it has a negative relationship. So we're going to look at now the tutorial. So that's our background information. So keep these things in mind. This multivariate linear regression, and then remember your dependent variables, your explanatory variables, or actually are independent variables in statistics, but in GIS we like calling them explanatory variables. We're going to try to interpret coefficients, what they mean, and then we're going to try to look for these kind of relationships, and we're going to try to make these relationships in common words. So here's the beginning of our tutorial. So in order to demonstrate how the regression tools will work, we're going to analyze 911 emergency data for Portland, Oregon metropolitan area. So, so as a community, our taxpayer dollars, or in this case, Portland's taxpayer dollars, are used to respond to emergency 911 calls. And so where you put 911 stations or substations, or how you respond to these calls can all factor how much it's going to cost. And there's limited funds, so you want to understand the relationship that crime has and how it's distributed over the community in order to best use that money. So so we're going to be using projections like, okay, as the population doubles in the next 10 years, how can we better respond to increased call volumes? And how do you plan for this? So regression analysis is often used as a planning tool. So questions like you can ask are, where are the hotspots? Which areas have low call volumes? How close are respondents to hotspot stations? So this handout you can find in our GWR folder, of course, which you can download from the blog under the assignments page. So here's GWR, you can download that. Once you download that, you'll have the same stuff, and you can follow along with this regression analysis handouts. So the first thing that we're going to be doing is going to, well, not in this case see spatial stats, but we're going to go to our regression analysis 911 call.mxt. That's our ArcMap document that contains everything. So we're just going to open this up. So I'm going to double click on that .mxt file, and ArcMap will launch. Okay, so now ArcMap is launched up, and you can see that the hotspot analysis data frame is active. You have here 3 data frames: regression analysis and prediction. Right now we're going to be working off of the hotspot analysis data frame, and you can see here it's saying to make sure that hotspot analysis is active. So it is active. So in the map, each point represents a single call into 911 emergency center. So if we look here, each one of these calls right here, this is the hotspots here. Each one of these dots represent a phone call into the emergency center. So I'm actually going to move this off the screen in order to make it easier to see, and I'm going to make this full screen and turn off my results. And this zoom layer here so we can see really well. So you can see each one of these dots are emergency phone calls. This is real 911 calls, representing over 2,000 911 calls in Portland. Whenever we expand here, we see response stations. That's what this green symbol is. You see we have 3 different response stations to 911 calls. And underneath is this surface that's been created underneath is a hotspot analysis tool, which was used to create this surface of where the most phone calls are taking place. You can see here in the red area, this is a hotspot with a lot of emergency responses, and the blue area is a cold spot, and then green. So these green crosses are the existing response stations. So you can notice that 2 stations to the right of the map are located on this one, for example, is located on a very hot spot. Here is located near a hot spot. But we can see here that this station is located in a cold spot. So we might want to investigate why this station is put here, as opposed to being placed somewhere closer to where the crime activity is taking place. So with this analysis, as a community, you can decide if having the station here is even worth it, maybe closing the station and moving it closer to the hotspot activities. So that's something, or you can think about adding a fourth station. So these kind of things can be debated using this kind of information of where the crime happens, the hotspot activities taking place in. So, seeing the data is pretty powerful, but next we want to explore why is this pattern existing? So the next question we want to ask is, why are call volumes so high in areas where there's hotspot areas? Why is there so many calls in this area? And we also want to think, what are the factors that contribute to this high volume of 911 calls? And so to answer these questions, we're going to use the regression tools in the ArcGIS. So if you go to the Arc Toolbox here, you can see that there's already some pre-prepared tools set up here for you, regression tools, spatial statistics, analyzing patterns, so forth, all these different tools that we can use. And we're going to want to go into the spatial statistic tools, the spatial statistics tools toolbox. And so one thing that we're going to want to do is set our environment settings. So we're going to click in this white space, and we're going to click on environments. This is setting up certain settings that are going to be set throughout the whole workspace. So we can always have the same kind of settings that are kind of defaulted. So one thing that we're going to want to do is change our current workspaces actually this is pretty good. We want to have them as the outputs in our GWR folder. If that doesn't already exist, you can just click on this option folder and then navigate to the desktop and then click on the output folder. That's one that we want to use, and you would click add. We can check out our coordinate system, make sure that it's set up into State Plane Oregon North FIPS. That's going to be the state plane system for Portland. That's probably the official projection for the city. And then for the processing extent, we can look here and we can see that we can set this to the same as data 911 layer calls. And all this is going to do is make sure that we do not process anywhere outside of this. So there's no reason to process outside of this extent. So once we have those settings set up, we hit OK. Now our environment for our toolbox, those settings are all set up in there. So one thing that's going to be a major factor is that we can't look at the 911 calls as points. That's not going to help us in the regression analysis. So they've been aggregated into census tracts, probably using a spatial join. And so you can look at the counts of the variables. So if you look at observed 911 data calls, like let's go and activate this layer here and see what's happening here. So if we look here at the observed the 911 data, you can see here all these dots. Each dot represents a 911 data call. But what we can do is spatially join those into the observed 911 data call, which has already been done for you. This is going to make these dots add into the census tracts. If I open up this attribute table here, you can see that we have information now like total population, what was the call rate in the population, jobs information, distance to urban center, different kinds of factors that we might think, alcohol, outlet densities, population densities, different levels of education. So all these things were brought from the U.S. Census, and we kind of took the U.S. Census data and this time added in number of phone calls that have taken place by basically doing a spatial join between this and the 911 data. The reason why we like using Census Track is because Census releases a lot of great information on the track level. They're not going to release it lower than that. So, but at the track level, we can kind of compare these Census measured factors to now our own measured factors of 911 calls. So as you look here, what kind of factors do you think would affect 911 calls? Maybe perhaps education level or unemployment level. Whether or not there's high populations or low populations or education levels of the populations. So like what about population level? You would expect there to be more calls where there's more people, right? So let's test that. Just call volume a simple function of population. The more people you have, the more people call 911. So if that's true, then we just say where's population going to grow, and that's what we put the call centers. So we're going to use our toolbox, and we want to navigate to modeling spatial relationships tools, and then we're going to go to the ordinary least squares tool, the OLS tool. So go ahead and double click that, and what you'll see here is your wizard for the tool. I always like running it with this tool help, so we can kind of see what's going on. But you can see here that ordinary least squares, it does a linear regression, and it tests what that relationship is. So you can see here the observed values are going to be these reds, and then the predicted values would be what happens from the linear regression. Ordinary least square is going to measure this residual. This little line here is the residual, and test that. So for our input, we're going to say observed 911 data calls. That's the data set we're using. For our unique ID field, we want to use unique ID. So this is going to help the computer, keep variables separate from each other. For our output, we want to go into our outputs exactly, and we're going to call this one OLS 911 calls. And you can see that the default way of naming is really long in ArcMap. So you're going to want to override how they're naming it and name it yourself as just OLS 911 calls. So I'm going to say save, and then so my dependent variable that I want to work with this time is going to be calls, right? So if we look back at our equation on page 2 or on page 1, our dependent variable in this case will be calls. And what we're saying our explanatory variable is going to be, in this case, population, to find out if it's a simple relationship with population. So our explanatory variable will be population. So we click on population. And so we go ahead and hit OK. We're not worried about this output report. Don't worry about that. And here's some additional options. We're not worried about that either. These would be good if we wanted to share with statistic packages, but in this case we're going to stick with ArcGIS. So we just go ahead and hit OK. Our process will run. We can check out in the results what's currently going on. You see ordinary least squares is running. We can always check out our messages here, since it tells us what's happening. So let that process run. And so whenever it's finished, it's going to give you, of course, this warning message, 0851. And it's just, they always give you these warning messages because it's so easy to make mistakes with regression analysis. Just telling you the results of regression analysis are only as trustworthy as the model and the data and the assumptions that you're using. So just be careful with the tools you're using. That's what the warning. So they have warnings on every single statistic that you do in GIS. So don't worry if you see the little warning sign. And then you'll see here some information about the different statistics that came out of the OLS measurement. And then we can look here and we can see our shapefile for our OLS. So you can see here, these are standard deviations from the predicted value. So this would be how off the value was. So red areas, for example, are going to be under-predicted. This is where the actual number of phone calls were higher than what the model predicted. Blue areas would be areas that were lower than what was predicted. So we can see areas of over-prediction and under-prediction, and see how that's clustered. We can see here a clustering of high predictions here, and a clustering of low predictions in these areas. And then these yellow areas are areas that kind of met near the average. The fact that we're seeing clustering happen kind of already shows us that there is some kind of pattern that's a little bit independent of population purely. Like we can see here by going and looking at our progress window in the messages, our adjusted R value was only 0.39. That means that population only was able to explain 39% of the cases of the 911 calls. So this indicates that population alone, if we use population as our only factor in our model, we would only be explaining 39% of the call volume. So we pretty much would only know 40% kind of confident, 40% of what's going on. So that's kind of a low R value for our model case. We want our model case to be much higher. So if we look back at our original hypothesis, we said that call volume is simply a function of population. And so, so we're saying, can we just predict where future 911 calls are based on population projections alone? And in this case, we're going to say probably not. Because if the relationship was between 911 and just population, we would say that we would have something like R value maybe near 80%, a lot higher. But that's not exactly what's happening. We only have 39% of the story being answered by population. So what we should say here is that we're not satisfied. We need other variables. So the next question that we want to ask is, what other variables should we use? And this is maybe the hardest thing to do in regression analysis, is trying to find all the key variables that you would use in explaining the model. So that's what the next step we're going to try to do, is try to find key variables. So next part, when we're trying to find key variables, we kind of just have to start making educated guesses. So what do you think might be part of this phenomenon? What's leading to it? Maybe the number of apartment complex, maybe the unemployment rate, maybe the income or education might predict 911 calls. We're not exactly sure, so we have to test whether they are good or not. So we're going to use a scatter plot matrix, because so we can graph and explore this relationship between call volumes and other candidate explanatory values. So we're going to use graphs. So what we want to do is go to our menu. So we're going to go to view, and we're going to choose graphs, and we're going to do create. So we're going to experiment here with the scatter plot graph. And so we're going to want to choose our, not OLS calls, but we want to select observed 911 data calls. And here we can start adding in different fields. So the first field you want to do is calls, because that's going to help keep the scatter plot reasonable. And then afterwards you want to say maybe population. You want to do maybe renters, so like maybe different things. You can add a fourth one. Maybe we say median income is a possible contender for scatter plots, for factors that lead to higher 911 call volumes. So whenever you choose the same, let's choose 4 of them. We hit next, and you'll see that it will prepare our scatter plots for us. So now we can kind of look at these different results and kind of see what they're doing. So if we look at, for example, back at our page number 2, we can see here what these graphs are looking like, with strong positive relationships, strong negative relationships, or no relationships. We kind of want to see which one has a closer trend to something like this, as opposed to that. Those are going to be the ones that have, better explanations. So we can look back over here and say, well, calls to median income. Kind of see that, it's kind of spread out. Calls to renters is, it's okay, but still, it's kind of concentrated here. But like here's something like renters to population, for example, has a really good distribution. But that's renters to population. That's not, in our case, it's not interesting. So let's hit back, and maybe we can try some different fields. So let's try calls, population, jobs. Oh, let's change that. Sorry, I meant to do observed data. So calls population. Instead of renters, let's do the jobs unemployment rate. Let's try lower education, low education level. How many people have low education level? And then let's see distance to urban center. How close is it downtown versus suburb and so forth? Let's try this out. So we're seeing here like high positive. If we imagine you put a line through here, it'd be highly positively correlated. Lower education seems to be a pretty good one too. Jobs here, there's some that are a little bit lower below it, but seems like it's okay. And population. So these are the 4 factors that we're going to want to go with. You can see this compared to, let's say, the overall distribution. It's really different. So we want to go with these 4 different factors in our model. So we're just going to hit finish, and we have our scatter plot here saved for us. So now we're thinking, okay, those are the 4 factors we want to do. Let's go back to our OLS and test that. So next thing, we're going to go back same way we were testing. Is it simply a function of population? Now we're going to ask, is it a function of population, jobs, education, and distance to center? So we're going to run our ordinary least squares, and then we're going to choose our observed 911 data calls. The unique ID field, again, on our outputs, we're going to call this, I'm going to say data 911 calls OLS. So data 911 calls OLS. And of course, you can choose any name you want. That doesn't really matter, the naming. Our dependent variable will be calls, right? And we're saying, okay, populations can explain calls, jobs can explain calls, lower education percentages, and distance to urban center. Those are the 4 factors that we think are going to explain calls. And we hit OK, and we let it run. So you can see ordinary least squares is running. If we go over here and check out our results, you can see our new results are processing right now. And then, of course, we get our warning message, watch out, you're working with statistics. But you can see here now, we can look at our ordinary least squares, and we can see our adjusted value now is 0.8, which is really a lot better. That means that we're now explaining with those 4 factors, we're explaining 80% of the variation that's occurring. In some cases, you can keep on testing different OLSs, so you can just go back here and on your results, scroll up, and a lot of times if you were doing this for a project or something, you can start checking on different boxes and seeing how that R value increases or decreases, and see which one's the best setup. But for now, we're just going to go with these 4 factors. We're saying that volume of 911 calls are going to be related to or explained by population, the job amount of the unemployment rate, the level of the percentage of lowly educated people, and the distance to the urban center. And so the next thing that we're going to want to test now will be the spatial autocorrelation. So we're going to want to see if the spatial autocorrelation is telling us that this is random or not for the under and lower predictions. Because you can see here in our OLS that resulted, we still have under and lower predictions. That's fine. Of course, no models can predict perfectly, and we're using standard deviations anyways. So there's always going to be lower and under prediction. The question that we want to know if this model is good or not is this standard or lower predictions, lower or upper predictions, under or over predictions, randomly distributed or not. Right now, when we look at this, it looks pretty random compared to our old one. You can see here from the old one. Let's give it a little bit of time to draw. You can see from the old one here that this was clustered. We can visually see it, but we could also test this idea, is it clustered with a spatial autocorrelation. So you see, we want to test if this standard residual is clustered or not. So what we're going to do is run a Moran's I, a spatial autocorrelation. So if you double click this one, you'll see what we're testing. Is it dispersed, or is it clustered, or is it random in the middle? So the input feature class we want to do is data 911 call OLS, the last one. Our input field, we want it to be the standard residual. And then for the distance, so we want to generate a report. And Euclidean distance is fine. Standard inverse distance is all these other informations here are fine. So we're going to hit OK. And our spatial autocorrelation will now run. So our spatial autocorrelation finished running. And if we look here in our results, we'll see the information come out. But what we want to do is look at the report. So if we look here in the results menu, it's telling me that on my desktop in the GWR outputs folder, I have my report. So let's navigate to that. Desktop GWR, outputs, and if we look here, we should find our Moran's Eye report. Having trouble finding it. And here it is, Moran's Eye results, and that's just in my output folder. So if I double click this, it's going to open it into my web browser, and we can see here that our predictions are random. See right here in the middle, random. That means that there's no significant pattern that exists, and that's great news to hear. That means that we are not having, that we're explaining all the factors that cause this distribution to happen. The rest of it is kind of a random error term, which is fine. So we have R squared value of over 0.8, which is great. Our spatial autocorrelation says this is at random. We looked at our scatter plots, and they looked nice. So we can now come here and say, you know what, we think call volumes are related to population, job rate, education level, and distance to urban center. So with this information, we can say, okay, we're ready to start actually modeling to do our models. So let's check now let's do one last check just to make sure everything's good. There's 6 things we have to check. Do the coefficients have expected signs? Do we have any redundancy in our models? Are coefficients statistically significant? Do we have residuals that are normally distributed? Do we have a strong adjusted R value? And are we having no spatial autocorrelation? So first thing, let's check the coefficients if they have the expected sign. So if we go into our results again, just make this a little bit bigger so we can see it. So we go into our results, expand this out, and we look at our OLS that we did. We can see here the coefficients. So for example, our intercept had a coefficient of 15, populations had a positive coefficient, so more people means more calls. That makes sense. Jobs, lower the job rate, the higher the unemployment rate, the more calls there are. The higher the lower education there is, more calls there are. And then distance to urban center. The further away you are from downtown, the less calls there are. So we expected all these signs to take place. So these all seem pretty reasonable for it to take place like this. So next we want to check between redundancy among our explanatory variables. This is inflation factors, variance inflation factors. So we want to make sure that they're not double counting each other. So if we look here at the VIF, which is the last one, we can see, of course, our intercept won't have anything, but these other values here, the other VIF values, what we want to look at. The cutoff number here is 7.5. So we can see here all these are 1.7 or 1.17, a lot lower. So they're a lot lower than 7.5, so that's great. But if we saw this having a 7.5 value or higher, we should start thinking we need to get rid of this variable because there might be some kind of interactions happening. Next, we want to make sure that all of our population, all of our variables are statistically significant, and you can see that with the stars here. ArcMap's nice and makes a little star next to the value to let you know that it is statistically significant. But basically, it's just looking at what the p-value is, saying if it's lower than 0.5. In this case, we're all way lower. That means we all have statistical significance for these. If we didn't have that, you would want to get rid of that factor in your GW. So next, we want to make sure that the residuals of over and under predictions were a result of random noise. We can check that by checking our Jarka-Bera test, which makes sure that it's not significantly significant. And we can see here this test is significantly significant. So I'm sorry, don't read it on G. This is just a note. We do not want this to be significant. So if the p-value is less than 0.5, we can see here's the results of the statistics. And it shows that with 2 degrees of freedom with our chi-squared and our value of 0.034, and that value is and then our value comes up to 0.84, we're not having statistical significance, which is good. We do not want statistical significance with this one. This will make our model biased if it was, and in the case that since we don't have it, we're good. Next, we want to check our adjusted R-square value, and you can see here our adjusted R-square is a 0.83. R-squared values can range from 0 to 1, measuring the variation. Generally, we're looking for 0.5 or higher, so that would mean a good R-squared value. In this case, our R-squared value is 0.8, so we're really in a good situation. And then our final one is to look at the spatial autocorrelation, and we go to our spatial autocorrelation here, and we saw from our report that we have things that are randomly distributed. So we're good on spatial autocorrelation. So we're ready for our GWR. So let's get to our GWR now. So we're going to go to our GWR tool. So that's our toolbox. We see our geographically weighted regression. We're going to open that up. And then for our input feature, we're going to do our data 911 calls, observed data 911 calls, this one. And then our dependent variable, we're going to choose calls. Our explanatory variables, we want to do population. We want to do jobs, low education, and distance to urban center. In our output feature class, we're going to want to put it here, and I'm just change the name to just GWR results.shp. Our kernel type, we're going to do adaptive. And in our bandwidth method, we'll use AICS. That's good. And our output cell size, instead of 30, I want to do 135. That's just the size of our raster grid. And then our coefficient raster workspace, I'm going to put this here, and I'm going to make a new folder called raster. Okay, so those are all my settings. Again, you can refer to the handout on page 17 for all the settings. Again, if we go back to page 1, you can see pretty much what we're doing here is we're saying calls is this one. These different X values are here, population, jobs, low education. We're going to calculate these different beta values. So we go ahead and hit OK. And we let it process. We can check out our results to see our geographic weighted regression going through. Whenever it finishes, it's going to output these different informations, the neighbors, the residual squares, so forth, our adjusted values. And we see our R adjusted value is very high at 0.87, so that's good. So GWR founded that we had 46 neighbors to calibrate. We have R adjusted value of 0.87, and so this is all good. So you can see here that the GWR that comes in, the shapefile that's produced defaults to mapping out the Okay, so since our OLS did show that our distribution of variables were random, that means that we have a good, we've done a good geographic weighted regression. You can see our spatial autocorrelation value was random, so that was great. So one thing that we can look at now is that we've had all of our, that on our output, we have these raster surfaces that have been created, and these raster surfaces map out the different coefficients. So if we look at our geographic weighted results and we open up the attribute table here, we can see that each one of them we have here is our predicted. So the way our model works is that same formula that we've been using on page 2 or on page 1. Right, so if we look at page 1 here, we can see y is our dependent variable is equal to these coefficients with our explanatory variables, right? These are explanatory variables and these are their coefficients. This model is pretty much represented here where we have our intercept, right? Our intercept here is going to be the coefficient of the coefficient of this right here, this B naught. Beta naught. The C1 of population, that's going to be our coefficient for population. C2 is our coefficient for jobs, and C3 is our coefficient for education. So these are, each one are the individual coefficients for that regression, and then it gives you your predicted value for each one of these polygon areas. So what's interesting is that we know that the coefficient for each one of these areas, we can look at they're interpolated over a surface, and whenever we turn off our regression analysis, our polygon, we see this raster, and this raster is going to show us this value interpreted. So you can see here the y-intercept value on this raster is very high in this area, very low in this area, just because of the way the raster is. So I can actually click on information, and I can see my intercept's very low here. Here it's very high at 23. So here the intercept is helping, has a higher value, higher value towards the model prediction. If I look at here, distance to urban center, here distance to urban center plays a very low role, right? Because it is the urban center. It plays a very low role in the model, while over here it plays a very higher role, impacting the model greater. So that kind of also plays, that's how we can visualize these coefficients. Here, education level, we can visualize that the distribution of the coefficients on education level is very different. So if I click here, this is going to have a higher coefficient than these areas over here. Let's see, this one has a lower coefficient. So the higher or lower the coefficient is, the greater it impacts the model. Basically, just imagine here, you see this y, this dependent variable, will be impacted greater by this x variable if this coefficient is very high. So the higher this beta 1 is, the more x1 is going to contribute to the y. The more it's going to influence the y. So these coefficients, their values, the higher they are, the more they impact this y output. So whenever we look at here, we can see how the coefficients distribute. They're not evenly distributed. We can see like there's some areas where it explains more of the y output than other areas. So let's focus on the education one. So if we go here and we turn off these other ones, we look at education, for example, And this changed this color ramp to a different color ramp that's maybe easier to look at. We can see here that in these areas, for example, that are green, these locations is where low education variable is a very strong predictor for 911 calls. While the areas like this one in red, these are going to be very low predictors, very weak predictors for 911 calls education levels. So this kind of shows that not every single variable has the same impact. So for example, here, let's look at jobs. Turn on jobs. The job rate is a very high predictor for 911 calls, while in other areas of the town, it's not. It doesn't really make that big of a difference. So if you're going to use like a policy, like maybe education scholarships to increase education in certain neighborhoods or something to try to lower 911 calls, this low education is not going to give you the same impact helping policies to change education levels and all throughout town. Only in certain parts where you see here it has a high influence. These red parts of town aren't going to have high influence. So this way you can target your policies to different areas or make projects, maybe like add a library here or something to help increase education levels in that area. So this is really great information for us, right? We know what areas, what the spatial relationship is like for education for 911 calls. We know what the spatial relationship is like for distance, urban center to 911 calls. All these things we have information about, right? But one thing we can also do is, so we can of course look at our model at any time. We can look at our model and we know that if we know the different factors that can, for any one of these polygons, we can use that to predict the amount of 911 calls. So if we know the X factors for any one of these places, we can use the coefficients to predict the Y. And that's where prediction comes into play. So for example, if we look here under this properties, under the attribute table on our GWR results, we can see here our observed is 6, but we have a predicted value of 14. So actually this was kind of off, but you can see here this predicted model is coming up with 14 when it plugs in these coefficients, okay, into these different variables here that we have under the 911 data observed. So you can see we can plug in now these variables like jobs, low education, distance to urban, multiply them by those coefficients, and we can actually predict how many phone calls are going to happen. So imagine we have a future time where those locations have changed. These locations, these different values here, education level or job levels have changed. How much change are we going to have in 911 calls or population grew? So let's test that with our prediction. So let's go to the table of contents. So this is right here, the table of contents. Let's go to our predictions and let's activate this one, this data frame. So that brings up this predictions data frame that's going to help us finish this lab. What we want to do is open up the GWR predictions model. So if we go to our toolbox, we can see here GWR with predictions. If I open this, edit, you have to right click and say edit, you can see the model. So we have our geographic weighted regression. These are going to go and we put in our call data and our prediction locations, and then we'll have here these different results are created. So go ahead and double click the GWR tool. Make sure you have call data, calls, yes, that's good. Our explanatory variables, we want those. And here we want to have our output to be results gwr.shp, that's good. Adaptive bandwidth parameter, which is having this error value. So here in our number of neighbors, we 150, predicted locations, additional parameters, predicted locations, so it's good. Everything's good. I'm not sure why this bandwidth parameters is showing up with this little red explanation, but let's hit OK and see what happens. So we're going to want to run our model now, so we'll go ahead and hit the run button, and it failed. Actually, if you go here and you switch it from AIC and then you switch it back to bandwidth parameter, it ends up working. Here, and let's just make this called 2. And so after everything seems nice, these are the different settings we want. Pretty much what it's going to do is going to take the the beta values and try to predict, in this case, not crime, but 911 calls. We hit OK, and our geographic weighted regression, we're going to hit run, and it's going to run through the model. So whenever the model is completed, you can see here run is complete. We can close this and go ahead and close that. And yeah, go ahead and save it. And you can see here that we're going to have now predictions versus the geographic weighted results. So here, predictions is what we're expecting to happen in our predicted values. So let's compare that with the 911 calls. So if you switch this over to list by drawing order, you can kind of rearrange this. And here's our GWR predictions, and here's our observed 911 calls. So let's bring this up here, and let's toggle on and off between the two. So you can see observed 911 data is what's currently happening. Predictions is what we're expecting to happen. So here's predicted, here's observed, here's predicted, here's observed. So what we see is an increase in these regions here for predicted more 911 calls. So even though right now these are like low spots for 911 activity, these predictions show that this area here is becomes a higher spot. So actually, whenever we go back and we look at our response stations where they're located, having a response station located here is very forward thinking. It shows actually that in the future, this area is going to have an increase in predictions, an increase in 911 calls that we should be worried, that we should think about. While these other areas, have maybe lower 911 calls, or actually maybe about the same 911 calls happening. So that's the difference. That's how we can predict with geographic weighted regression. So pretty much geographic weighted regression is a way for us to, one, analyze spatial relationships between two different data sets. Two, to use those to quantify those spatial relationships, to understand, which one impacts each variable more. And then 3 is to predict what's going to happen when things change. So whenever we create a model like this, and we make these coefficients, afterwards, if we change these explanatory values, we can try to predict what's going to happen when those explanatory values are changed. And this really helps in policy planning in order to in a way predict what the future crime rates are going to be like, future 911 responses are going to be like, so we can better place our stations. So these explanatory values, and we plugged in different explanatory values here, and then we got predicted 911 calls. So these are going to be predicted if the relationships stay the same. And basically that's GWR, geographically weighted regressions.